Now let's move on to our first problem of composite materials, which is problem number 5. So problem number 5 reads as follows. A large particle composite consisting of tungsten particles within a copper matrix is to be prepared. If the volume fraction of tungsten and copper are 0.7 and 0.3 respectively, estimate the upper limit of the specific stiffness of the composite, given the data in the following table. So there are two approaches to the problem. You can either do the modulus and the density separately using the simple rule of mixture and then calculate your specific stiffness, or you can calculate specific stiffness all in one step. So I'm going to show you both approaches. Both are correct. However, you'll notice that they yield slightly different values. So let's do approach 1. So approach number 1, we're going to calculate the modulus of the composite and the density of the composite separately. So for simple rule of mixture, the modulus of the composite is equal to the modulus of copper times the volume fraction of copper plus the modulus of tungsten times the volume fraction of tungsten. So that's going to be equal to 110 gigapascals times 0.3 plus 407 gigapascals times 0.7, and that's going to yield a value for the composite of 317.9 gigapascals. So that's the Young's modulus for this composite. Now let's calculate the density of the composite. That's going to be equal to density of copper times the volume fraction of copper plus the density of tungsten times the volume fraction of tungsten. And that's going to be 8.9 grams per centimeters cubed times 0.3 plus 19.3 grams per centimeters cubed times 0.7, and that's going to equal 16.18 grams per centimeters cubed. So now that we have our Young's modulus for the composite and we have our density of the composite, we can calculate our specific stiffness. So our specific stiffness is equal to the Young's modulus of the composite divided by the density of the composite, which is 317.9 gigapascals divided by 16.18 grams per centimeters cubed, and that's going to yield the value of 19.64 gigapascals. So our specific stiffness is equal to 19.64 gigapascals using approach number 1. So now let's move on to approach number 2. Approach number 2 uses a simple rule of mixture again, but we do it all in one step. So this is approach number 2. So we can say that our specific stiffness is equal to our Young's modulus of copper divided by the density of copper times the volume fraction of copper plus the Young's modulus of tungsten divided by the density of tungsten times the volume fraction of tungsten. And that's going to be equal to 110 gigapascals divided by 8.9 grams per centimeters cubed times 0.3 plus 407 gigapascals divided by 19.3 grams per centimeters cubed times 0.7, and that's going to equal a final value of 18.47 gigapascals. So the specific stiffness using approach 2 is 18.47 gigapascals. So we can see that using the two different approaches will yield slightly different results, but they are both correct and they would both be accepted on a test. So that concludes problem number 5. Now let's move on to problem number 6. So problem number 6 says, a continuous and aligned fibrous reinforced composite having a cross-sectional area of 970 millimeters squared is subjected to an external tensile load. If the stresses sustained by the fiber and the matrix phases are 215 megapascals and 5.38 megapascals respectively, the force sustained by the fiber phase is 76,800 newtons, and the total longitudinal composite strain is 1.56 times 10 to the minus 3 determine the following. A says the force sustained by the matrix phase, B, the modulus elasticity of the composite material in the longitudinal direction, and C, the modulus elasticity for the fiber and matrix phases. So let's deal with part A first. So part A wants us to find the force sustained by the matrix phase. Upon reading the problem, we immediately notice we are not given any volume fractions of either the fiber or the matrix. So we need to find a way to find one of the two and then be able to find the force sustained by the matrix. So reading the problem, we can see that we're given the force sustained by the fibers. We're also given the stress sustained by the fibers and the cross-sectional area. So given those three parameters, we are actually able to develop a formula to be able to solve for the volume fraction of the fibers. And we do so accordingly. So we can say that the stress of the fibers is equal to the force on the fibers divided by the area of the fibers. But we're not given the area of the fibers. We're given the area of the composite. But we can rewrite this as the force of the fibers divided by the volume fraction of the fibers times the area of the composite. And now you'll notice that we have the volume fraction of the fibers, which is what we're looking for in our equation. So let's rearrange this equation for the volume fraction of the fibers. So we can say the volume fraction of the fibers is equal to the force of the fibers divided by the stress of the fibers times the area of the composite. Let's substitute the values from the problem statement. So 76,800 newtons divided by the stress of the fibers, which is 215 megapascals, times 970 times 10 to the minus 4. That's now meters squared. And that's going to give us a value of 0.368. So we can say that the volume fraction of the fibers is equal to 0.368. So that's the first thing we need to do. Now that we have the volume fraction of the fibers, we can find the volume fraction of the matrix. So the volume fraction of the matrix is equal to 1 minus the volume fraction of the fibers, which is equal to 1 minus 0.368, which is equal to 0.632. So the volume fraction of the matrix is equal to 0.632. Now that we have the volume fraction of the matrix, we can do the same steps that we took coming to this point backwards and calculate the force sustained on the matrix. So we can say that the stress on the matrix is equal to the force on the matrix divided by the area of the matrix. Or we can say the force on the matrix is equal to the volume fraction of the matrix times the area of the composite. Rearranging this for the force on the matrix, we see that the force on the matrix is equal to the volume fraction of the matrix times the stress on the matrix times the area of the composite. And that's going to be equal to 0.632 times the stress on the on the matrix, which is 5.38 megapascals, times 970 times 10 to the minus 4, and that's again meters squared. And that's going to give us a force on the matrix of 3,298.16 newtons. So simply, the force on the matrix is equal to 3,298 newtons. And again, I want to remind everybody to change all their megapascals to pascals, all their millimeters to meters, and all of their forces to newtons, and this way all of the units will come out in the desired units that you're looking for. So now let's move on to part B. Part B wants us to find the modulus of elasticity of the composite material in the longitudinal direction. We know that the modulus of the composite is equal to the stress sustained by the composite over the strain on the composite. But we don't know the stress on the composite. However, we can say that the stress sustained by the composite is equal to the force sustained by the matrix plus the force sustained by the fibers all over the cross-sectional area of the composite. Now, if we combine these two equations together, we can easily solve for the modulus of the composite. Therefore, we can say the modulus of the composite is equal to the force sustained by the matrix plus the force sustained by the fibers divided by the cross-sectional area of the composite times the strain induced onto the composite. Now all we have to do is plug in our values and solve for our modulus. So we'll write 3,298 newtons plus 76,800 newtons divided by 970 times 10 to the minus 4 meters squared, and we plug in our strain of 1.56 times 10 to the minus 3. This is going to yield a value for the modulus of the composite of 52.9 gigapascals. And that's how you find the modulus of the composite in this problem. Now let's move on to part C. Part C wants us to find the moduli of elasticity for the fiber and the matrix phases respectively. So let's first do the modulus for the matrix phase. So the modulus of the matrix phase is equal to the stress of the matrix phase divided by the strain of the matrix phase. Now you're wondering, where are we going to get the strain of the matrix phase from? Well, because we're dealing with a longitudinally loaded composite that's being stretched in the direction of the fibers, we have an isostrain condition. And what isostrain means is we have the same strain on the composite as we do on the matrix and as we do on the fibers. So because of this isostrain condition, we can say that the strain of the composite is equal to the strain of the matrix is equal to the strain of the fibers. And therefore, we can write the modulus of the matrix is equal to the stress on the matrix divided by the strain of the composite. So we can write our stress on the matrix, which is 5.38 times 10 to the 6 pascals divided by 1.56 times 10 to the minus 3, and that's going to give us a value of 3.45 gigapascals. Therefore, we can say that the modulus on the matrix is equal to 3.46 gigapascals. Now, the last thing we have to do is find the modulus of the fibers. So the modulus of the fibers is equal to the stress on the fibers divided by the strain of the fibers. But again, because of our isostrain condition, we can simplify that to our strain of the composite. Substituting our values, which is 215 times 10 to the 6 pascals divided by 1.56 times 10 to the minus 3, we're going to get a modulus for the fibers of 137.8 gigapascals. And now that concludes the solution to problem number 6. Let's move on to our final problem of composite materials, which is problem number 7. So the design of an aligned and continuous glass fiber reinforced nylon 6/6 composite requires that the fibers carry 90% of the longitudinally applied load. Given the data provided in the figure below, determine the following. A, the required volume fraction of the fibers. B, the tensile strength of the resulting composite. And C, they want us to schematically draw the stress strain curve for the composite inside this graph. So part A wants us to find the volume fraction of the fibers. So we know from the problem that the fibers must carry 90% of the applied load, which means that only 10% of the load is going to the matrix. So let's express that ratio. So the force on the fibers divided by the force of the matrix is equal to 0.9 divided by 0.1. 90% going to the fibers, 0.9, which is 90% going to the fibers, and 0.1, which is 10% going to the matrix. That simply equals a value of 9. So we can now say that FF divided by FM is equal to 9 is equal to EF VF divided by EM VM, or we can further simplify to EF VF is divided by EM 1 minus VF. Now we can very easily identify our unknown parameter, which is VF, and in fact what we're solving for, and simply solve. Substituting the values from the problem, EF is equal to 72.5 gigapascals times VF divided by EF, which is 3 times 1 minus VF. Isolating for VF and rearranging the equation, we can get that VF is equal to 0.271. And that's how we find the volume fraction of the fibers for part A. Now part B says the tensile strength of resulting composite. So let's write down our tensile strength equation for a composite that's loaded in the longitudinal direction. So our stress of the composite loaded in the longitudinal direction is equal to sigma m prime times 1 minus the volume fraction of the fibers plus our stress star of the fibers times the volume fraction of the fibers. Now let's look at our graph and determine what these parameters are. So up here, this is our sigma star F. And if we follow that all the way down to the point of intersection of our matrix material, that's going to be our sigma m prime. And that's all we need. So let's substitute those values. We'll get 30 times 1 minus 0.271 plus 34,000 times 0.271. And that's going to give us our stress on the composite load in the longitudinal direction, which is equal to 940 megapascals. So far the problem has been very easy and very straightforward. The final thing we need to do is draw the curve corresponding to our composite material onto the stress strain curve, which is provided. So we know that composite materials generally show two different points. We have the first region, which is stage 1, and then we have stage 2 up into the point of failure. So this here, we can say stage 1, and this we can say stage 2. And now let's add the value which we just calculated, which is the stress on our composite, which is here. We can say that that's 940 megapascals. And that concludes this problem, and that actually concludes our section of well and composite materials. I look forward to seeing you all soon.